Run one stress test on a luxury tower in Dubai. Below the mechanical roof, the building is trying to hold 24 degrees Celsius. Up here, the surface reads 54 degrees. Then one condenser fan stops. For the first few moments, nobody inside has to notice. The marble lobby is still cold, the glass windows are still sealed, the environment remains completely controlled. But the cooling system has just lost part of its ability to reject heat. So, does the building wait for the roof to cool, or does someone climb into the heat to save the machine? And if the repair takes too long, what reaches its limit first? The machine, the technician, or the thermal capacity of the structure below? This is not a story about a single broken fan. It is an investigation into the extreme physical limits of urban engineering, where the margins for error shrink with every degree, and the battle against the desert relies on machinery that can never be allowed to stop. A single access door on a skyscraper roof separates two completely different physical realities. On one side, you have polished stone, seamless hospitality, and millions of people who expect uninterrupted comfort. On the other side, you have brutal solar radiation, superheated metal surfaces, and massive industrial machines fighting desperately to move heat from the inside to the outside. The authorities use specific design parameters for air conditioning systems. The standard calculations account for an outdoor dry bulb temperature of 46 degrees Celsius and an indoor target of 24 degrees Celsius. That massive thermal gap is the invisible foundation of the entire city infrastructure. To maintain this gap, massive amounts of thermal energy must be continuously gathered from the interior spaces and physically rejected into the atmosphere through complex refrigeration cycles. This means the most critical equipment must be placed in the most hostile location, which is usually the exposed roof. When everything operates perfectly, the system is invisible. You can travel from a climate-controlled airport terminal to a climate-controlled vehicle and into a climate-controlled shopping mall without ever confronting the reality of the geography. But this perfect machine requires an enormous amount of physical force to operate. The electricity required to run these chillers represents a massive continuous load on the power grid. Every degree of cooling requires a corresponding expenditure of energy. The building must constantly fight against the heat radiating through the glass, the heat generated by thousands of lighting fixtures, the heat emitted by computers, and the body heat of every single occupant. All of this thermal energy is pushed up to the roof. Heat is not automatically the failure point. The danger begins when the physical reality of the environment prevents the machinery above from performing like a new machine. The immediate defense against this environmental threat is that the engineers did not forget the desert. They fully understand the climate. Manufacturers build specific high ambient chillers designed to operate in extreme conditions. Some technical specifications for these industrial units state they can function in surrounding air temperatures approaching 55 degrees Celsius. Does that destroy the argument about physical vulnerability? No. It simply changes the nature of the question. A published operating range from a factory laboratory applies to a brand new unit in perfect condition with optimal airflow. It does not mean every unit installed across the city shares the same capability after 5 years of continuous operation. Designed for extreme heat does not mean immune to the physical consequences of extreme heat. The desert environment introduces multiple layers of aggressive mechanical degradation. Fine sand and dust constantly blow across the rooftops. This microscopic debris coats the delicate aluminum fins of the condenser coils. The moment those coils are insulated by dirt, the physical process of heat exchange is compromised. The machine loses a fraction of its efficiency. To compensate, the fans must work harder to pull more air through the restricted fins. The compressors must run longer to achieve the same cooling effect. The internal temperatures and pressures begin to constantly operate near their maximum safety limits. This physical degradation is relentless. The ultraviolet radiation bakes the insulation on the electrical wiring. The constant thermal expansion and contraction stress the copper piping. The safety margin engineered into the high ambient chiller begins to slowly evaporate, not in a single dramatic event, but through years of microscopic wear and tear. If a machine was carefully selected for extreme heat, how much operational margin truly remains after years of dust vibration and continuous peak demand? At 10 in the morning, a weak fan motor might just draw slightly more electrical current. At 2 in the afternoon on a record-setting summer day, that same motor becomes a desperate race against thermodynamics. The failure rarely starts with a catastrophic explosion. It starts with one component quietly reaching its physical limit. A single condenser fan has been spinning for hours under direct sunlight. The ambient air entering the machine is 46 degrees. The surface radiating heat from the roof deck below is 54 degrees. Inside the fan motor, the physical limits of lubrication and electrical resistance are being tested. The mechanical sound of the bearing changes slightly. The rotation becomes unstable as electrical resistance increases and the copper windings overheat, and then the fan stops. A well-designed modern chiller does not instantly destroy itself when one fan fails. It protects itself. The internal control system immediately detects the rising pressure caused by the sudden lack of airflow over that specific section of the condenser coil. To save the expensive compressor from critical structural damage, the electronic controller intentionally limits the cooling output. It might shut down one entire refrigeration circuit or modulate the compressor down to partial load. The machine survives the immediate anomaly. But a machine protecting itself means less cooling capacity is now physically available to the building. The control screen in the basement mechanical room registers a fault code. The available cooling capacity drops from 100% to perhaps 70%. If this occurred during the winter, this reduction would go entirely unnoticed because the thermal demand from the building is low. But this stress test is happening at the peak of the summer heat load. The glass facades are absorbing massive amounts of solar radiation. The cooling demand is at 95% of total design capacity, and the supply has just abruptly dropped to 70%. If the machine saves itself by reducing its output, who protects the building from the missing cooling? This physical gap between supply and demand is where the system begins to destabilize. The mechanical operations team is suddenly staring at a thermal deficit. They cannot manufacture cold air out of nothing. The heat entering the building envelope is now greater than the heat being removed. The fundamental physical balance is broken. The digital clock in the mechanical control room reads exactly 2:03 in the afternoon. This specific time introduces the most complex variable into the entire mechanical system: human safety limits. During the severe summer months, the occupational heat stress prevention policy restricts most work in open areas and under direct sunlight between 12:30 and 3 in the afternoon. This verified legal framework exists for a very strict biological reason. The combination of high ambient air temperature, intense solar radiation, and physical exertion can cause rapid physiological collapse. The restriction period is universally recognized as a severe hazard zone where the human body cannot safely regulate its own internal temperature. But the building management system does not recognize biological limits. The cooling capacity has dropped, and the internal temperature of the massive structure is threatening to slowly rise. The operations team must now answer a series of rapid calculations. How much redundant equipment is truly available right now? Is the mechanical fault stable, or will the increased pressure cause a second fan to fail? Can the thermal mass of the building absorb the heat until the sun begins to set? Does sending a technician onto the superheated roof create a greater physical liability than letting the indoor temperature drift upwards by 2 degrees? If the hottest hours of the day are biologically dangerous enough for the government to heavily restrict outdoor work, what does an urgent repair on an exposed commercial roof actually require? Does the facility wait for the ambient heat to weaken, or has the cooling system already started a physical chain reaction that cannot be reversed? The pressure on the engineering team is immense. The machine has sensors and automatic electrical shutdowns to protect its own internal components. But once a human being steps through that roof access door, who is monitoring the most vulnerable biological component in the entire chain? The number displayed on a weather application does not represent the full thermal load placed on a human body working on a skyscraper roof. When the technician steps out into the afternoon sun, they enter a multifaceted environmental hazard zone. There is the surrounding air temperature of 46 degrees, but that is only the baseline. There is intense direct solar radiation beating down from above. There is the relative humidity, which severely restricts the ability of human sweat to evaporate and cool the skin. There is radiant heat blasting upward from the 54-degree concrete and metal surfaces directly beneath their boots. Then there is the physical burden. The heavy fire-resistant clothing required for industrial electrical work traps body heat. The weight of the steel tools adds mechanical strain. And finally, there is the internal heat generated by the muscles while walking, kneeling, and pulling heavy metal panels apart. Reaching the machine is not the repair. The digital alarm only indicates that a circuit has tripped. It does not clearly explain which exact wire contactor or sensor caused the failure. The technician must now kneel beside the disabled fan, open a high-voltage panel, and begin a delicate diagnostic process. Would you remove a protective safety glove to feel if a motor casing is vibrating abnormally? Would you carry extra drinking water, or would you carry an extra heavy replacement part to save yourself a second trip across the scorching roof? How carefully and precisely can anyone trace an electrical fault while the brain is fighting an overwhelming physiological battle to shed heat? Cognitive function declines rapidly under severe heat stress. Decision-making becomes impaired. Hand-eye coordination drops. A misread voltage meter or a dropped screw extends the time spent in the danger zone. The human body is desperately pumping blood to the skin to release heat, leaving less oxygen for the brain and muscles. This is the hidden physical labor force that the system desperately relies upon. The entire stability of the building structure is resting on the shoulders of one individual trying to think clearly on a 54-degree surface. The fear does not come from a dramatic explosion. It comes from the terrifying reality that a small diagnostic mistake will increase the exposure time beyond the physical limit of the human heart and nervous system. The technician visually inspects the electrical supply lines. He examines the low-voltage control signal wiring. He physically attempts to spin the mechanical fan blade to check for seized bearings. Inside the dusty control panel, he finds a tripped thermal overload breaker on the fan motor circuit. This is a small bimetal switch designed to break the connection when the motor draws too much current and overheats. He presses the plastic reset button. A loud contactor violently snaps shut. The fan motor hesitates for a fraction of a second and then begins to spin. The digital alarm clears from the diagnostic screen. The technician quickly gathers his metal tools and retreats toward the conditioned air of the emergency stairwell. Down in the control room, the system parameters return to normal. The cooling capacity climbs back toward 100%. The crisis appears to be physically resolved, but a critical mechanical question remains hanging in the hot air. Did the manual reset actually repair the fundamental physical failure, or did it only temporarily bypass the warning sign? Electrical breakers do not usually trip without a physical reason. Was it a random voltage spike from the city electrical grid? Or is the copper insulation inside the fan motor beginning to melt and break down? If the motor windings are degrading, the motor will draw more electrical current as it operates, and it will inevitably heat up and trip the breaker again. This is the dangerous false victory that plagues complex mechanical systems under extreme stress. The physical repair work is not impossible. People successfully maintain cooling equipment through every summer. The danger is that extreme heat accelerates the degradation cycle. If the fan trips again in 2 hours, the technician must return to the roof. If the motor requires complete replacement, heavy lifting equipment must be organized, and the building must survive for days with reduced capacity. The pressure encourages temporary resets rather than deep physical diagnostics. Management wants the system running today, but physics does not negotiate with maintenance schedules. The tower might have another fan or another independent cooling circuit. But every piece of backup equipment is facing the exact same brutal physical environment. The concept of redundancy is the ultimate safety blanket for mechanical engineering. If Unit A fails, Unit B automatically assumes the thermal load. This sounds perfectly logical on a system schematic. But does redundancy actually eliminate the physical failure, or does it only buy a short window of time before the next component fails? When the primary fan stopped, the secondary fans had to spin faster to maintain the required airflow. The remaining compressors had to work harder to compress the refrigerant. The physical capacity reserve shrank instantly. Is a backup unit truly independent when it breathes the same hot air, collects the same blowing sand, and operates under the exact same solar radiation? If the extreme ambient conditions cause the first component to overheat, the backup component is immediately subjected to those exact same conditions, plus the additional thermal load transferred from the failed unit. This is the redundancy trap. Multiple pieces of equipment operating under the same physical stress tend to experience correlated failures. This is where the entire mechanical system becomes genuinely vulnerable. It is not that the building lacks backup plans, it is that backup capacity becomes most critical at the exact moment the environment is violently testing every single physical limit simultaneously. Some modern developments attempt to solve this by removing the chillers from the roof entirely. They use district cooling. A massive central plant produces chilled water and pumps it through miles of insulated underground pipes. This moves the heat rejection process away from the local roof, but it does not end the physical reality of the heat. The individual building still absolutely depends on a complex chain of energy transfer, heat exchangers, massive secondary water pumps, motorized valves, and hundreds of localized air handling units. The cooling machine may not always sit on the roof, but the chain still contains countless mechanical components that cannot all be allowed to fail. While the technicians anxiously watch the equipment temperatures fluctuate on the roof, what is physically happening 40 floors below in the occupied zones? The most dangerous stage of a systemic physical crisis often looks completely normal to the untrained eye. A stopped fan does not instantly turn a massive skyscraper into an oven. The building possesses massive thermal inertia. Thousands of tons of concrete, steel, and interior furnishings absorb heat, slowly acting as a thermal buffer. That is precisely why the opening stage of a cooling failure can remain entirely invisible. But the invisible nature of the threat is what makes it physically dangerous. As the cooling capacity remains restricted, the return air from the building spaces gets slightly warmer. The automated system tries to mechanically compensate. The chilled water valves open to 100%. The indoor supply fans ramp up to maximum speed, consuming even more electrical power and ironically adding the heat of the fan motors into the airstream. The operations team nervously watches the temperature sensors drift. Zone A is now at 25 degrees. Zone B is touching 26. The building controls begin issuing secondary warnings, indicating that the set points cannot be maintained. The operations team considers initiating emergency load shedding protocols, physically shutting off the cooling to empty corridors or back-of-house areas to save the primary zones. At what point does a routine mechanical warning become an undeniable thermal emergency? By the time the occupants begin to physically feel the heavy air and the sweat on their skin, how long has the mechanical system already been fighting a losing battle against thermodynamics? The machine may protect its own internal parts by shutting down entirely. The technician cannot physically work indefinitely under uncontrolled thermal exposure. And the building has thermal mass, but it does not have infinite thermal resistance. The first physical limit to be reached depends entirely on how much mechanical redundancy was built into the system, how quickly the root cause is diagnosed, and how safely the physical repair can be executed. But every minute the system struggles, the physical stress on the remaining components multiplies. The architects and planners who designed this infrastructure did not forget the heat. Their mathematical calculations already account for extreme outdoor conditions. Global manufacturers build specialized heavy equipment specifically designed for high ambient operation. The physics and the engineering can absolutely work. But they work only while the airflow remains unobstructed, the bearings remain lubricated, the electronic controls respond accurately, and trained human beings can physically reach the system when something inevitably breaks. That is the hidden machinery operating silently behind every cold glass facade and every glowing promotional video. The luxury tourism experience, the premium real estate values, and the entire economic model of the city depend on an interconnected physical cooling chain that is never allowed to stop. So, when a rooftop surface reaches 54 degrees, the real question is not whether the engineers have the technology to defeat the heat. The real question is how much the economy must continuously pay in massive electricity consumption, constant equipment, replacement, relentless maintenance, and intense human physical effort just to prevent the environment from winning. The illusion of effortless luxury requires a terrifying amount of physical force to sustain, and the cost of generating that cold air is rising every single year. This video is an analytical documentary based on verified engineering design parameters, thermodynamics, occupational health policies, and public data available at the time of production. The scenario presented is a realistic stress test designed to illustrate physical dependencies and environmental pressures, not a report of a specific historical accident. Economic conditions, tourism metrics, and environmental regulations are subject to change. This content is intended for educational purposes regarding urban infrastructure and physical systems. It does not constitute financial or travel advice. Some conclusions regarding system vulnerabilities are analytical inferences built from the cited engineering constraints.